Now let's study the second method for determination of focal length of a lens. I am talking about the auxiliary plane method. Okay, but before studying this method I will give you two basic principles which we are going to use. One of the principle is, if I have got a plane mirror and if a ray of light is incident normal on the plane mirror, so it will retrace its path. This is a very basic principle when you study reflection of light, that a ray of light incident normally on the plane mirror will get reflected along the same path. That means it retraces its path. That means if a ray of light after reflection retraces its path, then definitely it is incident perpendicular on the plane mirror. Second, if a ray of light after refraction through convex lens travels parallel to principal axis, that means from certain point the ray was coming and after refraction the rays are traveling parallel to principal axis, then definitely these rays are coming from the principal focus. These two basic principles you need to remember to determine the focal length of a lens by auxiliary plane method. So if I talk about first method, we have in this we have got two methods. So in the first method we have a plane mirror M, a convex lens L, we have a vertical stand and there is a fixture on the vertical stand which can slide up and down, okay, and we can lock its position, and on this fixture we have a pin. The pin over here serves as an object. So what we have to do, we have to look from above the pin. So this is the eye, so we have to look from above the pin and we have to move the pin up and down till its real inverted image is obtained without any parallax. What I mean to say is that if this is the object, okay, so the image can be obtained anywhere if you move it, right? So there will be a case where object and image will exactly coincide. See, you can see these conditions, that this pin being the object and this being the image. So this is nothing but the image of the pin. Okay. So what has happened over here? The rays of light coming from the pin, okay, will get incident on the lens and will get refracted, right, through the lens and will get reflected from the mirror. You can see the rays after refraction, okay, will hit the mirror, from where they will get reflected. So the rays coming from the pin are nothing but getting retraced. You can clearly see that this being the incident ray, this being the incident ray, okay. So the rays after reflection are retracing its path. Then definitely if the rays are retracing its path, the rays must have incident perpendicular, and you can see that if these rays are incident perpendicular on the mirror, then definitely these rays are somewhere traveling parallel to principal axis, and if the rays are traveling parallel to principal axis, then definitely they appear to be coming from its principal focus. So if you can obtain these conditions, then definitely the image of the pin will be exactly same size. You have to remove the parallax, that means you have to look above, at least at a distance of 25 centimeter from above the pin, so that parallax can be removed. You cannot obtain image like this. The image should be exactly coinciding. That means if this happens, that means rays from the pin getting refracted through the lens, then after striking the mirror again retracing its path, then definitely the pin is located at the principal focus of the lens. So how to measure this distance? So we can measure y, that is the distance of pin from the mirror. We can measure distance x, that is the distance of pin from the optical center of a lens. This distance are measured using a plumb line. That means the plumb, whenever you use plumb line, that thread on the plumb line is exactly vertical, and using a meter rule. So if I want to calculate the focal length of a lens by auxiliary plane method, I have measured two distances, y and x, and the average of the two distance will give me the focal length. So remember, the formula for the focal length will be x plus y by 2 simply. So if I use this method, the focal length of the lens is given by x plus y by 2, which is the mean distance of the pin from the mirror and the lens. We have got alternate method where we have a plane mirror. So I will show you that this is a stand, this is a rail where we have mounted some vertical stand. So this is a stand, this is the stand, this is the stand, and this is the meter rule where the marking is 0. Okay. On one of the stand I will fix a mirror, and you can clearly see. On one of the stand I will fix a lens L, and on one of the stand I will fix a pin. Okay. This pin serves as an object. So what I will do, either by moving the lens or by moving the pin. Okay, you can see here, this being the lens, this being the mirror, and this is the pin. So by adjusting lens or pin, again what we have to do, we have to obtain exactly inverted image of the pin which is coinciding, right? So if this being the pin, right, and this is the image of the pin, that means you can clearly see that the object and the image lie at the same point or they coincide, then definitely the rays from the object are retracing back. So what we can see from the ray diagram, the rays from the object after refraction through lens traveling parallel to principal axis, and somewhere they are incident on mirror. How? Perpendicular. Definitely if the rays incident perpendicular mirror, they will retrace the path, the ray will retrace its path. So the ray after retracing its path again will meet at O only. So the image I is obtained. So now the distance between pin and the lens is nothing but the focal length of the lens, because since object and image are at the same point, definitely the object is located at its principal focus, because the rays after refractions are traveling parallel, and I have explained you in this principle that if rays from certain point after refractions are traveling parallel to principal axis, then definitely they are coming from the principal focus. So if I have the distance x1 of the pin from the O, from the 0 of the scale, and if I have the distance x2 of the lens from the 0 of the scale, the distance between pin and the lens will be called as the focal length of the lens. So here what we can do, that to calculate the focal length of lens here in this case, so what I will do to calculate, I will simply do x2 minus x1. So by calculating the value of x2 minus x1 will give you the focal length of lens.